The next talk is by Miguel Montero, and he will talk about the DGKT scenario and the weak gravity conjecture. So the stage is yours.
Okay, thanks very much. Thanks also to the organizers for putting together a wonderful conference, and to all of you for listening. Particularly since it's the fourth day of the conference. So maybe we're all a little bit tired, particularly after the dinner yesterday and the partying afterwards. So because of that, I am gonna give you already the punchline of the talk first. Okay, so you can doze off if you so desire. So the title of the talk was the DGKT scenario and the weak gravity conjecture. The DGKT scenario is an interesting proposal constructed in four-dimensional supergravity for an ADS vacuum which has very small extra dimensions. It's very interesting. It's not fully controlled yet. There's some issues, and in deriving the solutions, you do some approximations that are not completely clear. So its 10 dimensions, its consistency as an actual string theory solution is not fully established yet. And the other part of my title is the weak gravity conjecture. It's a famous, or perhaps the most famous Planck conjecture. It basically tells you that in any consistent quantum theory of gravity, charged particles, strings, membranes must satisfy a certain inequality involving their mass or tension and the charges. And there's a lot of evidence for this conjecture. It has been checked in literally every string theory compactification. It has been shown to hold in every string theory compactification we've checked so far. And we even have proofs, for instance, in perturbative string theory or in this setup or another setup. So we have partial proofs. But there's no truly general proof for it, particularly in the case when you apply it to membranes, for instance, in 4 dimensions, to codimension 1 objects, to domain walls. Okay. So the punchline of my talk, the message that I want to get across to you is that these two things, the DGKT scenario and the weak gravity conjecture, two nice things, none of them 100% established, are actually incompatible. You can have both. Either the DGKT scenario is not a good, it's not actually a solution of string theory, or there is one vacuum which violates the weak gravity conjecture, which is the DGKT. Okay? So that's the gist of it. And so the plan of the talk is first I'm going to be telling you a bit more about this DGKT solution and what it is. Then how you can understand it in terms of brane probes and the weak gravity conjecture. And then I'm going to show you the tension between these two. Okay. So the DGKT scenario, the reason why we care about it is because it's an example of what is called a scale-separated vacuum. So what's a scale-separated vacuum? And why should you care? Why should you care about it? Well, it's easiest to describe what a non-scale separated vacuum is. So for instance, take ADS 5 process 5, famous holographic solution. There's a bunch of parameters. There's some ADS solutions. There's some curvature scale for the ADS. And there's a 5 sphere. And they happen to have the same size. The radius of the 5 sphere is the same as the curvature scale of the ADS. That's an example of what we call a non-scale separated solution. Okay, so the KK scale of the sphere is the same as the cosmological constant. And indeed, most holographic ADS solutions with an explicit top-down embedding that you might be familiar with are not scale separated. Okay, here's just a bunch of examples. And the interesting thing about having a solution which is not scale separated is that really you shouldn't think of something like ADS 5 process 5 as a 5-dimensional theory of gravity. You should think of it as a 10-dimensional theory because there's a internal space which is as big as the curvature scale of the external thing. So they are not separated. We do have some examples, top-down, very well-controlled examples, where you can achieve partial scale separation. For instance, ADS 3 crosses 3 cross K3 or T4, where you can make the K3 and the T4 very small. So if a non-scale separated solution is a solution where the internal space has the same size as the ADS factor, a scale-separated one is one in which some of the dimensions here are much smaller than the ADS scale. Okay, so they are like tiny extra dimensions. So these examples, they have achieved partial scale separation because the T4 and the K3 can be made very small, but there's no total scale separation because the S3 is always as big as the ADS3. This is another example that does that. And there are a few proposals in the literature that give you solutions which are fully scale separated, where the internal space is all of the extra dimensions are much smaller than the ADS scale. They're all proposals, and I'm going to focus on one of them. Now, the scale separation thing is important for a variety of reasons. First of all, if you want to use something like holography to try to connect with our universe, in our universe we only have 4 extra dimensions. So you're naturally looking for solutions which are scale separated. The extra dimensions are very tiny. And secondly, and more importantly actually, the scale separated ADS solutions are often the first step that we do in what we call uplifting, in trying to construct the sitter solutions, or solutions with positive vacuum energy, starting from ADS solutions. So it's very important to understand them properly, because there might be, if there's any issue with these guys, there's probably going to be an issue with the sitter constructions as well. So that's the general scale separated solution, and the DGKT vacuum, named so because of the authors of the original paper, is an example. It's perhaps the best understood, most controlled example of a scale separated solution. So how do we do this? Well, the DGKT vacuum is a 4D equals 1, ADS4 solution of massive type 2A string theory. That's type 2A string theory, where you turn on a 10-dimensional flux, Romance mass. And so how do you get it? What does it mean, this zero mode thing? Well, so the way you get to the DGKT solution is you start like in the green source Witten textbook, you take type 2A, you put on a Calabi-Yau space, that gives you a 4D equals 2 theory. Here I put ADS4, where actually is Minkowski if you don't turn on fluxes. And then you add orientifold planes that breaks to n equals 1. And it also induces a tadpole. There's some Yankee identity of the fields that you need to satisfy. And so if you have an O6 plane, you also need to turn on fluxes. So you can turn on Romance mass and H3 flux, and disappears in the tadpole here. So that's enough to cancel the tadpole without adding additional branes. So you do this in the DGKT solution. And then you are like, okay, fine, I have the type 2A supergravity equations of motion. I know what those are. I put these fluxes. I know what those are. And so in principle, I have a system of equations that I know how to solve. But solving the supergravity equations of motion, taking into account finding the profiles for every field in this crazy Calabi-Yau geometry, is very complicated. It's absolute hell. So in this paper, and the approach in many papers is actually very smart, to say, you know what, that's very complicated. What I'm going to do is I'm going to take the big 10D equations of motion, I'm going to integrate them over the internal space, and I'm going to get some equations of motion just for the zero modes, for the zero modes of the 10-dimensional fields. Okay? And this is what I solved, actually. Now, when I do this, I lose information. I don't have a lot of information about the higher dimensional theory, but it's good enough for me to find parameters like the cosmological constant. So in the DGKT solution, just like ADS factors S5 and every holographic background you're familiar with, there's an unconstrained flux, and the vacuum energy depends on it in some way. And so you can actually estimate the cosmological constant and the size of the extra dimensions, the size of the Calabi-Yau, and it's actually scale separated. Okay? So one is much smaller than the other. Great. The way I presented it, I think, is a bit clear what are the potential issues with this kind of thing. So we only solve the 4D equations of motion. So we are not sure that the thing that we do have actually makes sense. There's no explicit 10D uplift of the solution yet. And solving the actual problem is very complicated. And that's not the only problem. Like, how do I estimate the size of the KK scale? Well, typically what people do is like, I'm going to pretend there's no back reaction, there's no fluxes, and I'm just going to estimate it like that. But that estimate could be wrong, and there's examples where it's known to be wrong. And so, because of all these difficulties, there's a fraction of our community which for many years, it's a lot of people, have been thinking about the DGKT solution. Like trying to understand how does it work, trying to solve the 10-dimensional profiles of the fields in some perturbative series, and so on and so forth. So the story is still unfolding, but I think the conclusion is that there's no killer, okay? So we haven't proven for sure this is a good 10-dimensional, at least a good 10-dimensional background, but there's no argument that it doesn't. And if you're more interested in this topic, I recommend you have a look at this very nice review by Thibault Cordachet. This is precisely all about DGKT. So what I will do in this talk is I'm going to sidestep all of that complicated discussion. It's above my pay grade. And I'm going to assume that the DGKT thing is all right. And then, you know, if it's a fine solution, I get to look at brain probes of the solution. I get to put brains in the solution. And I'm particularly interested in brains that can change the fluxes in the DGKT solution. For instance, the Calabi-Yau that you use in DGKT has 2 cycles, and if you wrap a D4 brain on a 2-cycle, it extends, in the ADS factor, it sits as a constant radial coordinate. So here I have the Poincare patch, ADS in Poincare patch. So I have a D4 brain, which is at a constant radial coordinate. And remember, I told you there's this F4 flux in the DGKT solution. So what happens is that as you cross the brain, the DGKT, the flux changes by 1 unit. So this brain is interpolating 2 different members of the DGKT family of solution with different values of the flux. Okay? So you can put the brain there, and I'm just going to put the brain there, but I don't have any right, in principle, to just say that it stays there. This is string theory, it's quantum gravity, everything is dynamical. If you put the brain here, the brain is going to do something. It's going to have some dynamics. Maybe it's going to move to the right. Maybe it's going to move to the, okay, maybe it's going to move to the left. You know, it's going to do something. So, how do we figure out what the brain does? Well, you know, you find its equation of motion. How do we do that? Well, it's not difficult, really. So the dynamics of the brain, of this mode of the brain, is actually controlled just by 2 terms. One term is the tension of the brain. The brain has some tension. This is like the usual relativistic mass coupling. You know, m integral of ds is the action for a point particle. This is the action for a brain. And it also couples to the, because it makes this flux jump, that means it has to couple to the potential. So the exterior derivative of C3 is F4. So it also couples to it with some coupling, Q. And these 2 terms essentially determine the dynamics of the brain. And in this part.
Why are you not using DBI?
Sorry, what?
Why are you not using the full DBI?
Well, the full DBI would matter. You're very right. If I wanted to solve the actual equations of motion and find trajectories, I would need to use the full DBI, particularly when the brain gets a good speed. But I just want to know what's going to do a little bit. Where are the forces? I'm just studying the force balance here, and for that, this is enough. Okay? Well, no, I mean, the DBI action is exactly this term, square root of that of 1 plus the kinetic terms for the fields. So if you're just studying forces, you can ignore the kinetic terms, right? I'm just going to study the potential.
But there's a lot of times to couple the fluxes. It's not just the system. For the solution, you start from
In this case, the brain just couples to the F4. There's no other fluxes. You're talking about the additional Chern-Simons couplings of the brain, right? It doesn't. They don't. You're right, but they're not turned on in the solution for this particular configuration. Okay, so you have this thing, and you can actually. There's a bunch of simplifications. So in the end, the sum of these 2 terms is actually governed. If I'm only interested in what is the force that the brain feels, it actually comes down to this potential. Okay? So the tension term and the charge term, they have the same radial dependence, and so it's just something simple like this. You can actually show, using conformal invariance of the dual field theory, that it has to be R cubed. So that also matches the field theory result. So if you're here, then, you know, the dynamics of the brain depends on just what's the sign of this guy. And there's 3 possibilities. If the tension is less than the charge, potential is unbounded below, the brain is going to like to get to larger and larger radius. No? It's going to lower its energy by going to a larger radius, some sort of instability. And the DGKT solution is supposed to be an n equals 1 supersymmetric solution. So, well, just to finish, this case is inconsistent with supersymmetry. Okay? The potential has to be, is positive in a supersymmetric theory. If t is equal to q, the potential vanishes, and at least classically, this thing is a modulus. Okay? It's just, you can move the brain back and forth however you like. And if t is bigger than q, then the force is attractive. Well, we already ruled out one case just based on supersymmetry, or you could also do it based on unitarity of the dual CFT. And what I want to tell you is that the choice between these two possibilities is also regulated by something else, by a Swampland conjecture, which is the weak gravity conjecture. So what's the weak gravity conjecture? Weak gravity conjecture, today, I think there was either today or yesterday, there was a nice paper by Tom Rudilius on Archive, which is called Introduction to the Weak Gravity Conjecture, so that's probably a good place to learn about it. It basically tells you that if you have any quantum theory of gravity where you have a billion field strengths, like a billion P for field strength, there have to be branes which satisfy that its tension is lower than its charge in Planck units in a certain way. Okay, so that's the statement. And there's very strong evidence, and as I told you before, partial proofs of this, for objects of codimension bigger than 2. So for instance, particles in 4 dimensions, or strings in 5 dimensions. For instance, we have proofs in perturbative string theory. You can also try to derive it from CFT arguments. You can prove that it's true in every Calabi-Yau compactifications, in every solution with 16 supercharges. You know, we have partial proofs in big classes of examples, but no general proof. So I'm sweeping a lot under the rug, which this would, to tell you about the weak gravity conjecture completely, would be a 1 hour talk in itself. But something I want to mention is that in the case of codimension bigger than 2, we also have a nice heuristic interpretation of why weak gravity conjecture should be true. When the codimension is bigger than 2, you can also construct charged black branes, charged under a billion P for field strength. And then a heuristic argument is that, well, if you somehow believe that this extremal brane should be allowed to decay, then precisely the kinematic criterion such that a charged black hole or charged black brane can emit particles via Swinger effect is precisely that the weak gravity conjecture is satisfied. Now, what about codimension less than 2? So for instance, the case of domain walls is codimension 1, so it's here. Then there's no heuristic argument based on charged black branes. There's no charged black plane, but it's still true in many examples. For instance, D7 branes or D8 branes in type 2A. It was shown to be true in all Calabi-Yau compactifications of type 2 string theory, and it's certainly true in many holographic examples. So from the point of view of top-down constructions, it seems that the weak gravity conjecture also holds for these local dimension objects, even if the heuristic doesn't. Okay? So, going back to our potential, you can see how the weak gravity conjecture is relevant for this. It's literally telling you that T has to be less than or equal to Q. So the case T, so it's telling you that this case cannot hold. T bigger than Q, it's not true. So I forgot to say the weak gravity conjecture is not supposed to hold for every membrane or every particle of the theory, but there has to be at least one particle for which this happens. And so since the first case is not compatible with supersymmetry, as I said, how many cases are left that are possible and compatible with weak gravity? Very good. Kevin got it. Just the one, modulus. So a restatement of the weak gravity conjecture for membranes, which I don't think I've seen in the literature, although it's just a simple restatement, is that there must be an exact moduli space in the dual field theory. Why an exact moduli space? This brane, the coordinate of the brane, must mean something in the dual field theory, and indeed it corresponds to the web of some field in the dual field theory. So I am saying that this field must have an exact moduli space. Okay? So that's what the weak gravity conjecture is telling you. And this is a statement that you can just make directly in the CFT. It makes sense in the CFT. Now, this is true in many examples, in many top-down examples of ADS CFT, where the SUSY ADS is related to BPS branes, has BPS branes, and these are dual to the QFT moduli space. An example is 5 crosses 5. You can have D3 branes. They change the N, and that's dual to the fact that n equals super Jan Mills as a Coulomb branch. Beautiful. At the classical level, it's also true in the DGKT, because the D4 brane that I told you about before, I left the T and Q, I just left them as general parameters, but in this particular case, they actually match. So classically, this is BPS. However, weak gravity is supposed to be an exact statement. Okay? So when n equals 4 supergiant mills, you see that the moduli space of D3 branes is exact. You're not surprised because you say, oh, it has n equals 4 supersymmetry. That's so much supersymmetry. Of course, moduli spaces are exact. But things are weirder for this DGKT solution. Also, in this case, weak gravity tells you that the moduli space has to be exact. However, DGKT should be dual. It has way less SUSY. It's a 3D n=1 quantum field theory. And this is too little SUSY in general to protect the moduli space. Okay? Yeah, that's good. There's no holomorphicity. The action just comes from one superspace integral. There's no protected quantity. So in general, you would expect corrections to the potential. So how can there be a modulus? Well, one partial answer is that although 3D n=1 is not enough to give you a moduli space, if you have a parity symmetry, it turns out that the parity symmetry, because the superpotential is other than the parity symmetry, you cannot generate a potential for a parity even scalar, like this R coordinate. And indeed, there are some examples of 3D n=1 which have an exactly moduli space because they have this parity symmetry. This is an example. So sometimes it can work, but the only, at least certainly the only way that I know how to ensure the potential in 3D n=1 is protected against quantum corrections is to have a parity symmetry. So the question is, do we have a parity symmetry in DGKT? In DGKT, there's many fluxes. There's this F4 flux, this M flux, H3 flux. They all break the parity symmetry. So there's no reason for the D4 brane to be a modulus. So what we did is we went back to the original DGKT model. It's some Calabi-Yau orbifold, very nice, with very specific actions. We studied the D4 branes on this system, and we actually computed the low energy work volume gauge theory after doing the dimensional reduction for the D branes wrapped on Calabi-Yau, taking into account the orbifold and the orientifold. I'm going to skip the details. There's just a bunch of gauge fields in 5 dimensions from the D4 brane, and as you go to 3 dimensions, they give you something from dimensional reduction. Some fields are projected out by orientifold, some other fields are projected out by orbifold, and the resulting theory is 3D n=1, pure SU2, where the gauge coupling plus a modulus for the gauge coupling. So this is the action of the theory. And it was shown by Witten that this theory breaks supersymmetry spontaneously. It generates a positive vacuum energy, it generates a scalar potential, proportional to R cubed. I told you the result has to be always proportional to R cubed because of conformal symmetry, so that's a nice check. But anyway, it gives a positive vacuum energy. It gives a positive quantum correction to this quantity T minus Q. So what that means is that even though the brane is wrapping a BPS cycle, wrapping a calibrated cycle is the condition the brane is BPS only classically. Taking into account quantum effects, this brane is actually not BPS. So the weak gravity conjecture I told you is about just having one brane with this property. We checked all of them, so I'm going to skip the details. In every case, we found effects that leave the T minus Q, give a correction which is positive. So there's no brane with T equals to Q. There's a violation of the weak gravity conjecture for membranes, for objects with codimension 1. Okay? It just comes out of calculation in the DGKT background. You buy the DGKT background, you can compute these things reliably, and they show an inconsistency with the weak gravity for membranes. That means that force is attractive instead of repulsive. This adds to the weirdness of the DGKT solution. So as I mentioned, if you can prove the weak gravity for membranes, you show this thing is wrong. If you can establish the DGKT vacuum is fully consistent, you disprove the weak gravity for membranes. It has another implication, which is weird supersymmetry enhancements. So for instance, imagine you have something like the usual ADS5 cross Sasaki-Einstein 5 is dual to having some D3 branes over some singular Calabi-Yau geometry, and the whole thing is 14 equals to 2. In DGKT, the solution is supposed to be 14 equals 1. If it has some sort of holographic dual, which is branes probing some sort of cone geometry, we know that when you have the D4 branes floating around in the geometry, the thing is n=0, because the branes are no longer BPS. But when you put them on top of the singularity, they are supposed to be dual to the 4D n=1 DGKT solution. So there should be some sort of enhancement from n equals 0 to n equals 1, which is bizarre. Just as a final comment, if you want to look at scale-separated models which are okay with the gravity conjecture, there are some other alternatives which have parity symmetry. There's no explicit construction for them, although there's recent progress by Vincent van Hemmerlich. It seems, for this to work, you will need to find geometries which are very different from the known top-down string examples. And since I'm out of time, I'll just flash my conclusions. And that's the thing. Weak gravity and DGKT don't seem to be compatible with each other. Thank you.
Thank you very much for your talk. Are there questions? Yes.
Yeah, I have a comment and then a question. So the comment is, if you have branes in ADS, they're always fixed. The only example where they're not fixed, BPS branes, is the one that you gave, like the ADS 5 process 5. If they're the branes that generated the ADS background, these ones you can move around, but that's the only example. All other BPS branes are fixed. Even half BPS are completely fixed position. If you want to move them, you have to turn on the work volume flux. So as far as I can see, you haven't analyzed the case of work volume flux.
You can put them at any constant radial position that you like.
That's not true. The ADS has already potential. Just the ADS itself produces.
No. This is just like, for instance, in ADS factor says 5. Just go to the Coulomb branch of the unequal force per
Yeah, that's right? But this is because the D3 brane generated the background. It's not because it's BPS. It's because ADS 5 is the brane whose near horizon geometry gave the ADS 5. This is the only case where you can move the branes. If you take any other example, ADS 3 crosses 3, then you can have the D1, D5. If you put something, another D1, D5 system, you can move it around. Any other brane on that system is at a fixed position, even half BPS ones. If you want to move them around, suppose, for instance, in ADS 5 crosses 5, there are half BPS branes, which are ADS 3 crosses 2. These are at a fixed position. If you want to move them around, then you have to turn work volume flux, then you put the position somewhere else. That depends how much flux you turn on. So similarly here, the default brane is not the brane that generated this background. So it's not surprising. It's at a fixed position.
I'm just looking at branes that have a BPS condition. So there's no force.
But you're in a curved background. Have ADS. It's not the same as branes in flat space. Because it's a curve, because it's ADS, there's already a force.
I'm just looking at the ones that would be dual to a moduli space of the CFT if there was one. But anyway, we can talk further later if you prefer.
So there was
I have a question. So yeah, thank you for the talk. I think this is one of the best talks of the conference so far. I think. So at the end, you talked about the scale-separated solutions that are consistent with weak gravity conjecture. So does it are we able to make any statement regarding scale-separated CFTs because of this thing?
So you're asking if I can make a statement about scale-separated CFTs?
Yes. If there are some scale-separated CFTs, would they need to satisfy some constraints because of the constraints that you have here?
Well, I mean, this is very particular to the DGKT scenario and this kind of thing. In some sense, yes. Like the one thing that typically you want to have scale separation is to have solutions which have little enough supersymmetry. Okay, and because if not, there's an R-symmetry and there's a tower of states coming from the chiral primaries. And what I'm telling you is that these kind of solutions, they should not have the R-symmetry. Then they have these issues with getting a correction to the moduli space. So if anything like the holographic dual of DGKT exists, the conclusion would be like the weak gravity conjecture for members is not taking place here. I will say also that the dual to DGKT has very weird properties. So for instance, it has a central charge which scales like n to the 9 halves. That's much bigger than the biggest that we can do, which is, for instance, with the theory of M5 branes.
Okay.
which is NQ.
I see. Thank you.
Yes, there's a further question over there.
So if I understand correctly, you're claiming that you have a supersymmetric background and you wrap some brain on a calibrated cycle.
Yes.
And this is only supersymmetric classically, but not quantum mechanically.
That's right.
So can you explain what kind of, I didn't understand what kind of quantum corrections do this. So what's the parameter controlling the size of these quantum corrections?
So in this particular case, is the web of the dilaton. Okay.
But on the string or in the gravitational description, is it GS corrections? Or,
yeah, well, it's a GS correction. So essentially what happens is that you put the brain here in some two cycle. It goes to a three-dimensional gauge theory. And the gauge coupling of the three-dimensional gauge theory, which of course becomes very strong in the IR, is controlled by the value of the dilaton of the 10-dimensional solution. Okay, so it just turns on a non-perturbative effect.
Okay, here we have another last quick question.
Is it justified to ignore the Myers effect? It's related to the DBI action question.
So the Myers effect, for which so the Myers effect means that it would polarize because of the presence of other fluxes, of other Ramon fluxes.
But also the H3.
Yeah. Also the H3, that's right. Yeah, I think so. The calculation that I showed you here is really about the low-energy effective field theory of the brain. Okay? So it's just one D4 brain. So first of all, if it's just one D4 brain, typically it doesn't polarize, right? Or it's like a much stringy phenomenon. And I'm just looking at the low-energy effective field theory of this system. So it doesn't. Yeah, great. I was just going to say that if the effective field theory is 3dn equals 1 period U2, then that's what it is. And if having the brain being polarized a little bit, I don't see how that's going to change that. That's what I'm saying.
Okay, so let's postpone all other questions to the next breaks, and let's thank the speaker again.